Good morning, tensor friends. Um, in my studies of relativity, I keep flinging myself in front of the wheels of progress by asking the fundamental questions. And I've always been that way. I think that's why I was such a bad student. Why? Anyway, that's not the point. So I was using this yesterday, and I said, why does this Christoffel the symbol have this index in the contravariant position? And so I started digging into it. And once again, it turned out to be really simple. And it was fun. So I thought I'd share it with you. All right, let's start from the beginning. What is a basis vector? A basis vector is the partial derivative of a vector with respect to a coordinate. A perfect example is in plane polar, the coordinates. If I define a position vector of the polar coordinates superimposed on a Cartesian plane, I get this expression. I differentiate it with respect to r, I differentiate it with respect to theta, and I get two bases of the vectors of the vector, right? So then we ask ourselves, well, what happens if we take the derivative of a vector? How does a basis vector, change with respect to a coordinate? Well, that's what we're going to do. How does the basis vector change with respect to the coordinates? So we could differentiate the basis vector, this unknown basis vector with respect to a coordinate. So it's the ith basis vector with respect to the jth the coordinate. And you can express any vector. And by the way, the derivative of a vector is a vector. And we can express any vector as a linear combination of its components and the basis vectors. So we don't know what this is. And if we, as an example, in 3 dimensions, there would be 9. This represents 9 terms, right? So 1 divided by 1, 1 divided by 2, 1 divided by 3, 2 divided, etc. There would be 9 of these terms. And there could be a coefficient here, and we don't know what that is. So we want to write this in terms of Einstein's the summation notation. So we would write it like this. Now, since this is the derivative of a vector, it needs to be a vector. So we would assign it a unit vector, a basis to vector. And typically we assign the covariant basis vectors. And there is probably a coefficient here, and we don't know what it is, but there needs to be something there, right? Now think about this. Since this is a summation notation, we need to sum over this k. So what would we do? Well, we would put a k in the upper position here on this unknown thing, and you guessed it, that's where it comes from. Because we chose a covariant basis vector, we need something in the contravariant position to keep up with the rules of tensor calculus that we would sum over k. All right, so we figured that one out, and now we got to deal with what is this thing and what else does it need? Well, it needs some kind of indices to account for this, the partial differentiation of ith basis vector with the jth the coordinate. So we would just put those right in front of the question mark. And this question mark is called gamma, the Christoffel the symbol. So that's how easy it was to understand where that came from. Now, these are called Christoffel symbols of the second kind. Well, what about the first kind? What are they? And you guessed it. It's because we would choose a basis vector in this differentiation to start with a contravariant or dual basis to vector. So to keep up with the summation notation, we would have to have this in the covariant position or lower position. And this is a Christoffel symbol of the first kind. And why would you want these? I don't know. Because you probably would never start with a dual basis vector in doing calculations. There must be some reason you would. I don't know what that reason is. Anyway, I thought that was easy and it was fun, and I'll see you later.